Have you ever wondered what would happen if an interstellar visitor, some silent traveler of dust and ice, were to pass close enough to Venus to sprinkle its alien cargo into those clouds of sulfuric acid? Would the planet's furious winds, circling faster than any storm on Earth, tear those particles apart? Or, perhaps, would they transform them into something entirely new? Something the universe hasn't seen for billions of years? You see, Venus is not just a planet, it's a cauldron, wrapped in veils of acid and light. Its clouds float like layered oceans, 50 to 70 kilometers above a surface hot enough to melt lead. And within those swirling layers, the chemistry of life and death plays out in ways that we're only beginning to imagine. Now, imagine a fragment from far beyond our solar system, 3I Atlas, a comet made of frozen water, carbon monoxide, hydrogen cyanide passing through that inferno of mist and light. What happens when the chemistry of the deep cosmos meets the most hostile skies in our neighborhood? Well, tonight, that's the thought I want to explore with you, not as a statement of fact, but as a scientific what if, a thought experiment grounded in what we know and guided by curiosity. Could such an encounter stir up strange new compounds in the Venusian atmosphere? Could it create fleeting traces of molecules that whisper stories about life's raw ingredients, tested in acid and fire? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So, let's continue. Venus. Well, Venus is often called Earth's twin, but you see, that's only in size and gravity. In spirit, it's something else entirely. If Earth is a cradle, green, gentle, and filled with oceans that breathe, then Venus is the furnace left burning after the forge has gone cold. Its atmosphere is a monument to heat and pressure, and the deeper you look, the more it feels like standing before the gates of an ancient engine that never stops roaring. At about 50 kilometers above its molten surface, the world begins to change character. Up there, the pressure eases, the heat softens. The air thickens into endless banks of yellow-white clouds made of sulfuric acid dense, swirling curtains that hide everything below. That is where the light of the sun diffuses into a perpetual amber glow, where shadows vanish and horizons melt. You could almost imagine drifting through it, suspended in that golden haze, if not for the acid eating at the walls of any ship daring to linger. The clouds of Venus are layered, like the pages of an unread book. There's the lower cloud deck, dark and heavy with droplets, where temperatures climb close to the boiling point of water. Above that, there's the middle layer cooler, thicker, where the droplets grow smaller, more delicate. And then, finally, the upper haze, at about 70 kilometers, a thin veil of mist where sunlight meets chemistry. It's here that ultraviolet light from the sun breaks apart molecules, triggers reactions, and writes the ever-shifting code of this planetary laboratory. Now, these clouds, they aren't just clouds. They are oceans turned upside down. Instead of water vapor rising and condensing, it's sulfuric acid cycling endlessly, forming droplets, merging, evaporating, condensing again. The whole system breathes, but its breath is poison. It's not just acidic, it's hyperacidic, a place where even the toughest life from Earth would be dissolved in seconds. And yet, there's something compelling about that persistence, about a planet that has found its own form of balance in the middle of chaos. When you look at Venus through a telescope, it seems so calm, smooth, bright, almost serene. But that's an illusion. Beneath that beauty lies motion. The air spins around the planet at terrifying speeds. The winds race at more than 300 kilometers per hour, circling the planet in just 4 Earth days. That's what scientists call superrotation. It's not just a breeze, it's a global conveyor belt, a hurricane wrapped around an entire world. And the remarkable thing, is that no one fully understands why it happens. You'd think a planet's atmosphere would move roughly in step with its rotation, but Venus laughs at that expectation. The planet itself spins so slowly that a day on Venus lasts longer than its year, and yet the winds tear across the skies with furious speed. It's like watching a sleeping giant breathing storms in its dreams. The chemistry of that air is just as strange. It's mostly carbon dioxide, thick, choking, crushing. Mixed into it are vapors of sulfur dioxide, droplets of H2SO4, traces of hydrochloric acid, water vapor, carbon monoxide, and a scattering of other molecules. And, at every level, those chemicals interact in ways that defy intuition. Light splits them apart, collisions stitch them back together. The cycle repeats endlessly. Venus, in a way, is not a static planet. It's a chemical symphony that has been playing for billions of years. The upper clouds are where sunlight does its most delicate work. Photons from the sun strike molecules of sulfur dioxide and water, and the reactions give birth to sulfuric acid droplets. Those droplets, small at first, grow and merge until gravity pulls them lower, into warmer regions, where they evaporate and begin again. It's not just weather, it's alchemy. The planet is, forever distilling itself, and if you go deeper, below the clouds, into the dense layers of carbon dioxide, the pressure climbs swiftly. By 35 kilometers, the pressure is already like being hundreds of meters under the ocean. The air would crush metal, melt lead, and cook flesh in an instant. The light fades, scattered and bent until it becomes an orange glow that seems to come from everywhere and nowhere at once. It's like standing inside a sunset that never ends. The surface of Venus, well, it's not a place for delicate instruments or fragile dreams. Probes have survived there only for minutes before their circuits failed. The rocks are dry, the soil is baked to dust, and the air itself could tear apart the molecules of life as we know them. And yet, something in that brutality draws us in. Because where there's energy, chemistry, and time, there's always the question, could something, anything, have taken advantage of it? It's easy to think of Venus as a closed system, a place where chemistry has settled into equilibrium, sealed off by heat and pressure. But that's not quite true. The atmosphere is restless. It circulates, vertically and horizontally. Updrafts lift material from lower levels. Downdrafts carry processed gases downward again. So, in a sense, it's a giant mixer, constantly blending its ingredients. That's why some scientists describe it as a closed chemical loop. Over geologic timescales, everything that forms is destroyed. Everything that rises eventually falls. The planet eats its own history. But just imagine if something foreign were to enter that system. Some dust, some molecule, some fragment from beyond. The winds would seize it immediately. The currents would carry it through the planet's layers, blending it, dissolving it, transforming it. Within days, that tiny alien particle would become part of Venus itself. Its chemistry would be rewritten by the planet's furnace-like breath. And, it makes you wonder what new compounds could emerge from that violent meeting. What unrecorded molecules might flicker into existence for just a moment before, vanishing into acid and light? You know, the idea of hell has always fascinated humanity. Fire, pressure, suffocation, it's a primal image. And yet here it is, made real on a planetary scale. But the more we study Venus, the more we see that its hell is not just destruction, it's transformation. It's a place where elements are constantly reborn, where the line between solid, liquid, and gas blurs into something fluid and dynamic. There's also a strange symmetry between Venus and Earth. Both formed from the same dust, the same solar nebula, orbiting the same star. Both started with water, with volcanoes, with skies thick with carbon dioxide. But where Earth cooled and oceans formed, Venus heated up, trapping its gases in an unstoppable feedback loop. It's not just that one became paradise and the other a furnace, it's that both are expressions of the same cosmic experiment, two outcomes of the same beginning. So when we talk about Venus as a stable hell, what we mean is that its violence is predictable, almost elegant. Its storms are steady, its chemistry self-regulates, its surface may be deadly, but it's also constant. And, that's rare in the solar system. Most worlds change quickly, collapse, or freeze. Venus endures. It's been burning at the same intensity for hundreds of millions of years. You can trace that stability in its layered clouds, in their precise vertical structure. The upper haze, thin and reactive. The middle layer, dense and rich with droplets. The lower deck, darker, thicker, where light scarcely penetrates. The temperatures there shift gradually, from about -30 degrees Celsius at the top to almost 200 degrees near the base. And through all of it, the winds never stop. They circle the planet eastward, dragging with them waves and eddies, shaping the flow of heat and matter. It's this combination heat, acid, motion that makes Venus so scientifically irresistible. Because, well, in systems that are stable yet dynamic, chemistry becomes creative. Molecules find pathways, form fleeting patterns, evolve toward equilibrium only to be pushed away again by light or turbulence. And that's where the beauty lies. Not in what Venus destroys, but in what it creates, for a heartbeat of cosmic time. When probes like Akatsuki looked at these clouds through ultraviolet filters, they saw strange, dark streaks, bands of unknown material that absorb sunlight. No one knows exactly what causes them. Some think they're sulfur compounds, others suggest iron chloride. A few even whisper about complex organics, though that's still speculation. Whatever they are, they seem to pulse with the rhythm of the planet's winds, drifting and reshaping like thoughts across the surface of a dream. And, there's something deeply poetic about that. These clouds, full of acid and violence, might still hold secrets of chemistry we haven't yet encountered. They're not lifeless, they're restless. They process everything that touches them: solar radiation, volcanic gases, maybe even the occasional cometary grain. Venus, in its own way, is constantly performing experiments, running reactions, testing possibilities. So, when we speak of its layers, those 50 to 70 kilometers of atmosphere, we're not just describing structure, we're describing history. Each layer is a record of transformation, a memory of heat, pressure, and time. And perhaps, one day, when we send new probes to drift through those clouds again, we'll find traces of interactions that tell us not only how Venus lives, but how it responds to what falls upon it. Because you see, if one day an interstellar object, like 3I Atlas, were to pass near this world and deposit its dust, it wouldn't land on a passive target. It would meet a living system of chemistry, a cauldron waiting to rewrite whatever it receives. The clouds would seize it, churn it, break it apart, and perhaps, just perhaps, create something new. And that's the thing about Venus. It's not just a world of destruction, it's a world of reaction. Every molecule is caught in motion, every layer in dialogue with the one above and below. The planet is both furnace and laboratory, both memory and experiment. And as we, drift deeper into its mystery, we begin to see that its hellish calm isn't the end of the story at all. It's the beginning of something else. Something that leads us naturally to wonder about the next question: how those furious winds, those global currents, might take whatever enters and scatter it across the planet in just a few days. And, well, that's where we'll go next. The winds of Venus, well, they are unlike anything else in the solar system. You see, they do not simply blow, they race, they whirl, they engulf the planet in motion so vast and continuous that it becomes difficult to tell where the air ends and the world begins. When we speak of Venus, we are speaking of a planet wrapped in an ocean of storms, an atmosphere that doesn't just move around the planet, but outpaces the planet itself. That's what scientists call superrotation, a strange and powerful phenomenon where the winds circle the globe in just about 4 Earth days, while the planet underneath takes 243 to complete a single slow turn. It's almost comical, isn't it? The ground beneath moves like a whisper, but the sky screams. The planet turns lazily, as if trapped in deep time, while its atmosphere races ahead, restless, impatient. It's not just motion, it's contrast. A dance between stillness and speed, between weight and lightness. And, what's fascinating is that we don't yet fully understand why it happens. We can describe it, we can measure it, but the reason the engine behind it remains a mystery hidden somewhere in the chaos of Venus's clouds. Imagine standing at the top of those sulfuric seas at 70 kilometers up, where the winds begin their endless circuit. There's no solid ground, no horizon, just a churning expanse that moves faster than any hurricane on Earth. The clouds stretch and twist, and the light bends through them, scattering into soft golds and deep oranges. You wouldn't hear the wind, you'd feel it, a pressure on every surface, a grip that never releases. And down below, far beneath those endless waves of vapor, the planet itself spins the other way, as if trying to pull back what the atmosphere has already stolen. Superrotation isn't just a storm, it's a global conveyor of heat and chemistry. The equator, the poles, the day side, the night side, all are linked by this massive circulation. When sunlight strikes the upper clouds, the air warms and rises, creating high-altitude winds that race eastward. Meanwhile, the cooler air from the night side sinks and flows back underneath. The result is a vast engine, a system that redistributes energy so efficiently that Venus's poles are nearly as warm as its equator. The planet, it doesn't just spin, it breathes. But there's something else, something subtle. These winds don't move evenly. They pulse, they oscillate, they ripple with waves, planetary waves, gravity waves, Kelvin waves that roll through the clouds like invisible tides. Each wave carries energy and momentum, transferring it from one layer to another, feeding the superrotation. It's not a single mechanism, it's a collaboration of chaos. And, when you think about it, that's quite poetic. The balance of forces on Venus comes not from order, but from turbulence. For decades, spacecraft have watched these motions from afar. Pioneer Venus, Venus Express, Akatsuki. Akatsuki, in particular, gave us haunting images, the ultraviolet patterns that drift across the clouds, forming dark ribbons and bright streaks. These aren't mere shadows, they're fingerprints of the winds. Scientists tracked them, measured their speed, and discovered that at high altitudes, some parcels of air move at nearly 100 meters per second. That's fast enough to carry a molecule of gas completely around the planet before the sun can set. And, the deeper you go, the slower things become. At lower altitudes, closer to 50 kilometers, the winds drop to a crawl, perhaps a few meters per second. Below that, the atmosphere grows so dense, so heavy, that motion becomes sluggish. It's as if Venus stores its fury near the top, in a layer of freedom just above the oppression of its deeper air. The planet's violence, it seems, lives where light still reaches. There's a kind of eerie symmetry in that. The upper clouds, wild and fast, the middle layers, dense and brooding, the surface, crushed and still. It's like watching a storm fade into silence as it descends through time itself. And yet, somehow, all these layers remain connected. A pulse in one affects the others. The superrotation doesn't just skim the top, it drives the entire vertical structure of the atmosphere, pulling and twisting until everything moves in unison. What's so astonishing, is that even after decades of study, we can't pinpoint exactly what sustains it. Some say it's thermal tides, waves of heat caused by the day-night cycle. Others point to planetary waves born from the planet's shape, or perhaps to the interaction between sunlight and cloud opacity. It might be all of them, working together. It might be none. It's as if the planet guards its secret, allowing us to glimpse the mechanism but never touch the heart of it. And this, I think, is where Venus begins to feel alive. Not alive in the biological sense, but alive in its movement, in its restlessness. The entire atmosphere acts like a living being, circulating, adapting, adjusting. It carries energy the way a bloodstream carries heat. It transfers momentum the way lungs draw and release air. It's not just fluid dynamics, it's vitality. And, perhaps that's why we're drawn to it, because in the chaos of Venus's winds, we see a reflection of our own persistence against entropy. Now, the beauty of this superrotation is not just in speed, but in consequence. You see, if something, say, a molecule of dust or a fragment of cometary ice were to enter the Venusian atmosphere, it would not simply fall. It would be seized by these winds, spun around the planet again and again, mixed into its layers before it ever had a chance to settle. That means Venus, despite its density, is astonishingly efficient at stirring. Nothing remains local for long. Every drop of material becomes global almost immediately. That's why scientists often call Venus a planetary blender. Anything that enters its upper atmosphere, whether volcanic gases from below or cosmic material from above, is swept into a loop that circles the planet in just a few Earth days. Within a week, a trace of something exotic could be carried halfway around the world. Within 2 weeks, it would be everywhere. It's as if the planet refuses to keep secrets. But, well, that also means that any chemical reactions that happen there, any transient molecules formed by sunlight or collisions, are spread out before they can vanish. So even brief reactions leave faint echoes that instruments might detect as anomalies in the planet's spectrum. And that, is where the science becomes thrilling. Because those signatures, those tiny blips of unexpected light, could tell us not only about what's in Venus's air, but also about what happened to it. Think of it this way: the winds are both the messenger and the mask. They reveal by distributing, and they conceal by blending. The chemistry of Venus is shaped by motion, and the motion is sustained by chemistry. Sulfur dioxide absorbs sunlight, warms the upper layers, drives convection, and keeps the cycle alive. Without that, the winds would slow, the air would stagnate, and the planet's heartbeat would fade. Akatsuki's observations, gave us glimpses of that heartbeat. Its ultraviolet imager showed patterns of light that shifted over time, waves, eddies, turbulence. And from those changes, scientists reconstructed the structure of the winds, realizing that Venus's superrotation isn't static. It breathes, sometimes faster, sometimes slower. Sometimes waves from the lower atmosphere push upward, disturbing the flow. Sometimes the pattern smooths out again. It's like weather on a planetary scale, predictable in rhythm, but unpredictable in detail. And there's something deeply humbling about that. We often imagine planets as fixed, solid, almost eternal. But here, on Venus, the surface, we see the cloud tops are always moving, always renewing. The planet we observe tonight is not quite the same as the one we'll see tomorrow. It's not just alive, it's improvising. Now, if we step back for a moment, we might realize that this superrotation has another role. It erases memory. On Earth, winds and oceans create local climates, regions of difference. But on Venus, the air moves so fast, so thoroughly, that local differences cannot survive. The planet's atmosphere is homogenized, chemically, thermally, dynamically. Every molecule is shared, every anomaly diffused. It's not just a storm, it's a system of forgetting. That, has profound implications for how we search for clues of any foreign material, any external visitor. Because whatever arrives, dust, vapor, molecules, it won't stay where it lands. It will be caught up in this planetary carousel. And yet, if we can trace the patterns of motion, if we can model how the superrotation mixes materials, we might still detect the fingerprints of something that doesn't belong. It's astonishing to think that the relentless circulation, this constant storm, could also be a mechanism of preservation. By spreading materials evenly, Venus prevents them from being destroyed too quickly in one place. A molecule broken apart by sunlight on one side might reform in the shadowed air of the other, a balance of destruction and renewal. The planet is, both the predator and the protector of its own chemistry. Scientists have even proposed that waves generated by the planet's terrain, yes, even under all that air, might reach upward, like echoes of mountains in the wind, and contribute to the motion above. That idea came to life when Akatsuki observed a massive bow-shaped wave stretching across the atmosphere, fixed in place over the planet's highlands. Imagine that mountains you can't see shaping winds 100 kilometers above them. It's not just motion, it's memory, written in air. And so, Venus's superrotation is not one single phenomenon, but many tides, waves, convection, turbulence all dancing together. It's a reminder that even the most alien worlds are governed by principles that, in their complexity, mirror life itself. Systems that seem chaotic often find their own kind of order. When I think of it, I imagine that if an alien dust grain from some passing comet were to fall into this hurricane world, its story wouldn't end, it would begin. It would be swept along, dissolved in acid, irradiated by sunlight, yet carried and reshaped by the rhythm of the winds. It would, in a way, join the heartbeat of the planet. And that brings us, naturally, to another question. If such a visitor, say, 3I Atlas, were to meet Venus, what would it bring? What fragments, what frozen molecules, what ancient chemistry from the edge of interstellar space could it deliver to these clouds of acid and fire? Well, that's what we're about to explore next. When we imagine an interstellar visitor, something like 3I Atlas passing through the solar system, well, it's tempting to think of it as a story from long ago, a wandering ghost of ice and dust gliding through the void. But these objects are very real, and, they carry with them the chemistry of entire star systems. They are archives of the early universe, fragments of what happens when gravity and cold conspire to form the building blocks of worlds. So, when we ask what such a visitor might bring to Venus, we're really asking what the universe itself has been saving in its pocket since time began. A comet, you see, is not just a ball of ice. It's a layered relic, part frozen water, part carbon dioxide, carbon monoxide, methane, hydrogen cyanide, and a dusting of metals and silicates. The tail we see when it approaches the sun, that long luminous veil, is not light, but loss, the slow release of those ancient compounds into space. And, each one of those molecules tells a story. Water, for instance, is the memory of hydrogen and oxygen, forged in the first stars. Carbon monoxide and dioxide are the breath of dying stars. Hydrogen cyanide, HCN, that strange, simple molecule, is one of the universe's most versatile building blocks. It can, under the right conditions, lead toward amino acids, toward the chemistry of life itself. So, what would happen if a fragment of such material brushed against the veils of Venus? The super-rotating winds we spoke of earlier would capture it immediately, but before that, the comet itself, 3I Atlas, if we take it as an example, would have been shedding material long before it arrived. When comets near the inner planets, their surfaces awaken. The frozen gases locked inside sublimate, turning to vapor and bursting outward, dragging dust and grains into space. Around the nucleus, a glowing coma forms a vast halo of molecules and microscopic particles. That coma can stretch hundreds of thousands of kilometers, fragile and diffuse, yet dense enough to leave a chemical signature in the path it crosses. If, by coincidence or alignment, Venus were to pass through even a wisp of that coma, its atmosphere would encounter something extraordinary. Tiny grains of cometary dust, no bigger than a grain of sand, carrying mixtures of frozen water, carbon monoxide, and complex organics, would rain down through the upper clouds. And, because Venus's air is so dense, these grains wouldn't survive long. The friction would vaporize them almost instantly, releasing their contents into a storm of acid and sunlight. But that's where the story becomes fascinating. The molecules released HCN, H2O, CO, CO, CO2, wouldn't simply vanish. They'd mix, react, dissolve into droplets of sulfuric acid, or, collide with sulfur dioxide, and form fleeting compounds that might never exist anywhere else. The question isn't whether the cometary material would survive, it's whether it would transform, because, well, that's what Venus does. It transforms everything that touches it. When we look at comets like 67P Churyumov-Gerasimenko, studied by the Rosetta mission, or interstellar ones like 2I Borisov and 3I Atlas, we find remarkable similarities. Their comae, those shimmering halos, contain not just simple gases but also chains of organics, formaldehyde, acetylene, methanol, and traces of nitriles. Hydrogen cyanide is among the most consistent. It's found in nearly every comet observed, and it's astonishingly reactive. On Earth, in the right conditions, HCN can participate in pathways that lead toward amino acids or nucleobases, the scaffolding of genetic material. But on Venus, in a bath of sulfuric acid and ultraviolet light, the fate of HCN would be quite different. Still, that's the beauty of it. Chemistry doesn't ask for comfort. It asks for opportunity. The collision between cometary material and the Venusian clouds would not be gentle, it would be catalytic. Droplets of acid, heated by the sun and stirred by the winds, would trap foreign molecules, perhaps even stabilize them for brief moments before breaking them apart. And, that's enough. In chemistry, moments are everything. The dust component of a comet, though less glamorous than its ices, is just as important. Those grains are a mix of silicates, carbonaceous material, and metals, iron, nickel, magnesium. They're small, often coated with organic films. If even a fraction of those entered Venus's atmosphere, some would vaporize, releasing atoms that could serve as catalysts. Nickel, for instance, has long been known to accelerate certain reactions involving carbon monoxide and water, the so-called water-gas shift reaction. And, imagine that playing out not in a lab, but in the upper clouds of Venus, under the glow of an alien sun. The thought is strange, isn't it? That a dust grain born around another star could fall into the clouds of Venus and, for a few fleeting moments, act as a tiny laboratory where acid, heat, and cosmic memory collide. And yet, we know this isn't entirely hypothetical. Every year, Earth sweeps through the trails of ancient comets, collecting micrometeorites that contain just such materials. They dissolve in our oceans, mingle with our atmosphere, and sometimes even catalyze reactions we barely notice. So, perhaps Venus, too, is a collector of cosmic debris, performing its own experiments in silence. The tail, or more precisely, the coma of 3I Atlas, would have been rich in water and carbon-based gases. Water, though fleeting in Venus's skies, would play a crucial role. When vaporized, it would mix with sulfuric acid and sulfur dioxide, briefly altering the local chemistry of the clouds. Even in minute amounts, water can shift reaction pathways. It can introduce hydrogen, change acidity, form transient hydroxyl radicals that open the door to new reactions. It's not just the quantity that matters, it's the possibility. And hydrogen cyanide, that haunting molecule, would behave differently. In the ultraviolet light of Venus's upper atmosphere, it would photodissociate, split apart, forming CN and H radicals, which could then react with other gases. In a sense, HCN acts like a spark. It initiates cascades of chemical events, some destructive, others creative. In laboratory simulations, under acidic and high-energy conditions, these radicals can form more complex organonitriles, precursors to amino acids. On Venus, where sulfur compounds dominate, such pathways might lead instead to exotic sulfur-nitrogen compounds, molecules that could only exist in that fiery equilibrium between acid and sunlight. Comets also carry carbon monoxide and carbon dioxide, two molecules that seem dull but are endlessly important. On Venus, CO is rare and reactive. If introduced, it could undergo oxidation, photolysis, or even combine with hydrogen from water to form formaldehyde or methanol. Each of these reactions would be short-lived, yet in aggregate, they could create a subtle, measurable fingerprint in the planet's atmosphere. Astronomers might see it as a faint excess of carbon-bearing gases in the infrared spectrum, a whisper of something that wasn't there before. Then there's dust. You can't talk about comets without dust. The fine particles shed from the nucleus carry with them metallic traces, iron, nickel, cobalt, magnesium, all bound into mineral grains. These metals, when ablated into an atmosphere, form vapor that cools into microscopic oxides or sulfates. And, those vapors don't just vanish. They can seed clouds, change droplet chemistry, or even absorb sunlight, altering the planet's radiative balance. On Earth, we call that meteoric smoke. On Venus, it would be something far more alien, a rain of stardust dissolving into acid. What makes this idea so alluring is its scale. A comet doesn't need to collide with Venus to leave a mark. Even a near pass could sprinkle its material across millions of square kilometers. And because the planet's winds are so efficient, that material would spread rapidly, transforming from a narrow stream into a global haze. Within days, the signature of an interstellar visitor could become part of the entire sky. And, while the molecules themselves might vanish, the memory of their reactions could linger in shifts in light absorption, in subtle changes to the reflectivity of the clouds. It's easy to forget, but comets like 3I Atlas are messengers from beyond the solar system. They formed around other stars, in other clouds of dust and gas, and were thrown outward perhaps by passing giants, perhaps by gravitational tides. For billions of years, they drifted between stars, collecting radiation, losing volatiles, hardening into crusts of frozen carbon and metal. When one finally enters our neighborhood, it carries a sample of chemistry older than the Sun itself. To imagine that such a fragment could brush against Venus, that it could briefly share its molecular history with our nearest neighbor, is to imagine a moment when two stories of creation intersect. And there's something deeply human in that, isn't there? We, who are made of dust and water and light, looking at a world of acid and stone, asking what might happen if another wanderer of dust and water and light were to touch it. It's not just curiosity, it's recognition. It's the feeling that the cosmos, in its vast indifference, sometimes writes poetry through collisions. The coma of a comet, well, it's not steady. It breathes. As the nucleus rotates, jets of vapor burst from its surface, forming spirals, waves, and plumes. Each carries different ratios of gases, more CO2 here, more HCN there. So, if Venus were to pass through the outer regions of such a coma, it would encounter not a uniform cloud, but a shifting landscape of chemistry, some regions richer in carbon, others in nitrogen, others in metallic dust. The encounter would be brief, a few hours, perhaps a day, but the consequences could last much longer. We know, from past cometary encounters with Earth and Mars, that even small interactions can deposit measurable amounts of material. After certain meteor showers, instruments detect spikes in metals, like sodium and iron in our upper atmosphere. These fade quickly, but while they last, they alter the way our air glows in the night. On Venus, the same would be true, only magnified by the density of its air and the violence of its winds. Every grain, every molecule, would become part of a planetary scale experiment. And, maybe that's the point. When we imagine 3i Atlas crossing paths with Venus, we're not proposing an event, we're proposing a question. What would a world of acid do to the chemistry of life's ingredients? Would it destroy them utterly, or would it twist them into something new, something resilient enough to exist in conditions we once thought impossible? The evidence, suggests that even in the most hostile places, chemistry finds a way to keep going. In laboratory tests, amino acids and organics exposed to sulfuric acid can survive far longer than expected. The universe seems reluctant to let go of complexity. And that thought, that perhaps even Venus, in its searing hostility, could momentarily host the whispers of cometary chemistry, is enough to make us look again. Because the more we learn about comets, the more we realize that they are not just messengers, they are bridges. Bridges between the cold, dark, and the burning light, between formation and decay, between one world and another. And somewhere, between those bridges, lies the story of Venus, the story of what happens when a world of fire meets a traveler of ice. And, well, to understand what truly happens when that contact occurs, we have to look not at the chemistry alone, but at the mechanics, the physics of entry, of capture, of motion through an atmosphere thick as the sea. Because what happens to cometary matter when it meets Venus depends on more than composition. It depends on velocity, on drag, on energy, on the way particles slow, stop, and mix. And, well, that's where we'll go next. When something falls into Venus, well, it doesn't fall the way it does on Earth. You see, the air is so thick, so heavy, that it feels less like a sky and more like a sea. Imagine a grain of dust, a particle from an interstellar comet, like 3i Atlas, rushing toward that pale planet, wrapped in clouds. It's moving fast, maybe tens of kilometers per second, its atoms shivering from the cold of deep space. But as it meets the Venusian atmosphere, the story changes instantly. There is no gentle descent, no quiet drift. There is impact, compression, heat, a collision not with a surface, but with a wall of gas dense enough to stop a bullet in a few breaths. The first touch happens high above, the clouds, around 150 kilometers up, where the air is still tenuous, still thin compared to Earth. At that altitude, the incoming grain begins to slow. The atmosphere grabs it molecule by molecule, each collision a spark, each friction a wound. The surface of the particle heats, glows, and sometimes vaporizes entirely. Larger fragments might survive longer, shedding their outer layers in a glowing wake. The smaller ones, they barely make it past the first few kilometers before they're gone, dissolved into vapor. But that vapor doesn't disappear. It mixes, it merges, it becomes part of the air. And that, well, that's where the real chemistry begins. You see, the physics of entry is also the physics of transformation. Every collision releases energy, and every bit of that energy can drive reactions. In the upper atmosphere of Venus, where ultraviolet light beats down endlessly, that energy joins the constant pulse of radiation, stirring the pot of molecules that swirl in perpetual motion. And, because the winds move so fast, the vaporized remains of cometary dust don't simply linger in one spot. They are immediately swept into the global circulation, carried around the planet in days. Let's imagine one of these grains more closely. It's small, less than a millimeter across, perhaps a mix of ice and mineral dust. When it enters Venus's atmosphere, it begins to melt, then evaporate. If it contains metals, iron, nickel, magnesium, those atoms may ionize, forming a glowing trail. If it carries water ice, the vapor released encounters sulfur dioxide, forming sulfuric acid droplets almost instantly. So the act of entry itself creates micro-laboratories in motion, tiny pockets of chemistry ignited by heat, cooled by the dense air, and scattered by the wind. And it's not just the composition that matters, it's the shape, the mass, the velocity. A heavier particle will fall deeper before stopping. A lighter molecule, say, a bit of carbon monoxide or hydrogen cyanide, will slow higher up and drift with the winds. The atmosphere acts like a sieve, sorting material by its willingness to yield to pressure. Heavier dust grains might reach 40 or 50 kilometers before dissolving. The lighter gases, could be carried deeper, into the heart of the clouds, where temperature and pressure make new things possible. Venus's upper atmosphere, around 70 kilometers up, is where sunlight and chemistry meet in a constant duel. There, the air is thin enough for radiation to penetrate, but dense enough for molecules to collide. When an external particle enters that zone, it experiences drag that grows exponentially. Its velocity drops from kilometers per second to meters per second in just moments. The energy it carries, kinetic energy, is converted into heat, into light, into chemistry. And that, is why even the smallest intruder leaves a trace. It's not about size, it's about the moment of surrender. If we could see it, if we could somehow float there and watch, it would look like a brief rain of invisible fire. Each particle flares faintly, invisible to the human eye, but rich in ultraviolet and infrared emission. The droplets of acid respond, they absorb the vapor, they trap ions, they grow heavier, fall slightly, evaporate again. The whole process, from entry to equilibrium, might take minutes, or maybe hours, but in those minutes the air becomes something new. It's not just Venus anymore, it's Venus plus memory, Venus plus the echo of another world. The upper cloud decks act as both barrier and cradle. They stop most foreign material from reaching the deeper layers, yet they also provide the perfect environment for temporary preservation. Think of them as filters. What's too heavy sinks, what's too volatile rises, what's reactive becomes part of the haze. The droplets, tiny spheres of sulfuric acid, serve as chemical hosts. When vapor from a cometary particle meets them, reactions can occur on their surfaces. In laboratories, we call this heterogeneous chemistry, where gases react on liquid or solid surfaces rather than in the open air. On Venus, that might mean the formation of sulfur salts, nitriles, or even metallic sulfates. But what decides how deep something goes? It's a balanced cross-section, velocity, density, and the sheer will of physics. The denser the atmosphere, the stronger the drag. The smaller the particle, the greater the deceleration. At some point, every intruder reaches what physicists call terminal velocity, the speed at which drag equals the pull of gravity. On Venus, terminal velocity is astonishingly low. A grain that would fall through Earth's air like a pebble would drift here like ash through syrup. It's not just falling, it's sinking, slowly, softly, into a sea of acid and heat. Now, Imagine that instead of one grain, an entire stream of material enters hundreds, thousands of tiny particles from a comet's tail. They spread out, forming a diffuse sheet that drapes across the planet's atmosphere. Each particle slows, releases vapor, and then disappears, but the effect is cumulative. For a few hours, or maybe days, Venus's air would carry a faint excess of certain elements: hydrogen, carbon, nitrogen, oxygen, metals. These anomalies would swirl around the planet, following the same path as the superrotating winds. And, if we had instruments there, spectrometers or probes, they might detect these subtle fingerprints. A tiny increase in water vapor, a brief rise in hydrogen cyanide, a faint alteration in the optical depth of the clouds. Evidence not of collision, but of encounter. The deeper layers of the atmosphere, between 50 and 60 kilometers, are where conditions are strangely Earth-like temperatures, near room level, pressures similar to what we feel at sea level. If some of the foreign material and managed to reach this region, it might linger, it might dissolve into droplets, or adhere to them, forming complex compounds. The droplets could then fall lower, into hotter layers, where they would eventually evaporate, releasing their contents once again. And so, the cycle continues. Material enters, sinks, transforms, rises, and vanishes. Venus's atmosphere, behaves like a living system of exchange. Nothing truly stays still. When we think of capture, we might imagine holding something, trapping it. But on Venus, capture is dynamic, it's participation. The planet doesn't simply grab the incoming material, it absorbs it, processes it, and folds it into its constant motion. What survives is not the particle, but the effect, the chemical echo it leaves behind. There's another layer to this story, though. As the particles slow and warm, they generate shock waves, tiny bow shocks that ripple through the air. Those shocks compress and heat the local gas, sometimes triggering short-lived plasma states. In those conditions, molecules can ionize, and ions can combine in ways they never could in calmer air. For instance, carbon monoxide could react with atomic oxygen to form carbon dioxide. Hydrogen cyanide might fragment into CN and H, which could then bond with sulfur species to create exotic compounds like thiocyanates. It's chemistry driven by motion, by fall, by the act of surrendering to gravity. And it's not just the fall, it's the aftershock. Once the motion ends, the chemistry lingers. The energy released into the surrounding air continues to stir reactions long after the particle is gone. It's as though the atmosphere remembers being struck. And, in that memory, molecules rearrange themselves into forms dictated by heat and light and time. There's a poetic symmetry in it, really. A visitor from another star crosses light years of silence, only to be unmade in the embrace of a planet's sky. Yet, in being unmade, it leaves behind traces of its origin, and those traces, atoms of nickel, carbon, hydrogen, begin to play by new rules. They no longer belong to the comet, they belong to Venus. The moment of entry is not destruction, it's assimilation. If we could map it, if we could trace the path of each molecule from entry to dissolution, we would see a graceful choreography of energy. Some molecules would stop at 80 kilometers, trapped in the high haze. Others would fall to 60, merge with droplets, ride the Hadley cells downward before evaporating near the cloud base. Still others, lighter, more agile, might rise again on warm currents, joining the endless circuit of the planet's winds. So in that way, even a brief encounter leaves a long-lasting pattern, a chemical fingerprint stretched thin across the whole sky. And perhaps, that's how we should think of capture on Venus, not as a single event, but as a process that unfolds through layers of air and time. The atmosphere doesn't hold on to things, it transforms them. It doesn't bury, it recycles. That's why scientists often call it a closed chemical loop. Nothing leaves easily. Even light gases like hydrogen, which might escape eventually, must first pass through countless reactions, countless transformations, before they can slip away into space. So, what begins as a simple fall becomes a complex conversation between matter and motion, between what enters and what already is. And in that conversation, Venus reveals itself as more than a world, It becomes an alchemist, a place where chemistry and physics merge into one long process of translation. What comes from the stars becomes, briefly, part of a planetary story. And, well, when we follow that story further, when we ask what happens to those captured molecules as they're bathed in light and acid and heat, we find ourselves on the edge of another mystery. Because, you see, once the dust settles and the gases spread, the sun begins its work. Ultraviolet radiation tears bonds apart, drives new chains of reactions, and turns those traces of interstellar chemistry into something even stranger. And, well, that's where we'll go next. Light, well, light is both the destroyer and the creator in the clouds of Venus. It's strange to think about, isn't it? That the same sunlight that gives warmth to Earth becomes a scalpel in the air of Venus, cutting, breaking, rearranging the bonds of molecules as if the planet were a great laboratory suspended between fire and shadow. When cometary material, dust, water vapor, carbon monoxide, hydrogen cyanide drifts into that luminous atmosphere, it doesn't remain itself for long. The sun reaches for it immediately. Ultraviolet photons slice through the thin upper haze, and, in that instant, chemistry begins again from zero. Venus's clouds, at about 60 to 70 kilometers above the surface, are a battleground of light and acid. The droplets there, tiny floating spheres of concentrated sulfuric acid, are surrounded by gas molecules that never stop colliding. The ultraviolet light from the sun provides the spark, breaking bonds, creating radicals, atoms and fragments with unpaired electrons that crave new partners. You can almost imagine the chaos, every photon a blade, every collision a chance encounter. And, from that chaos, order emerges, at least for a moment, as new compounds form and fade, their lifespans measured in seconds. Take water, for instance. If even a trace of H2O from an interstellar visitor were to mix with the Venusian air, it would be instantly pulled into this photochemical dance. Ultraviolet light would strike it, splitting it apart. H2O becomes O, the hydroxyl radical, and atomic hydrogen. The OH radical is astonishingly reactive. It hunts for sulfur dioxide, forming sulfuric acid. And so, the introduction of water doesn't cool or soften Venus, feeds its acidity. It doesn't bring life as we know it, but it amplifies the planet's relentless chemical metabolism. And then, there's carbon monoxide, CO, a simple molecule, but one that, changes everything. When CO absorbs ultraviolet light, it can photolyze, breaking into carbon and oxygen atoms. Those free atoms don't stay single for long. They react with nearby molecules, carbon with sulfur, to form carbonyl sulfide, oxygen with CO2 to make ozone-like species. These processes happen in flashes, invisible but constant. Every second, in every cubic centimeter of air, thousands of reactions begin and end. Venus, you see, is not a still world. It's a chemical storm. Hydrogen cyanide, HCN, is perhaps the most intriguing of all. On Earth, it's a molecule of danger and of potential. It's both a poison and a precursor to life. In the Venusian sky, under ultraviolet bombardment, HCN doesn't last long, but the fragments it produces, CN, NH, CH, are fertile. They can form chains, combine with oxygen or sulfur species, and give rise to organonitriles molecules that, for a fleeting moment, contain both carbon and nitrogen in delicate balance. And, that's the kind of chemistry that hints at complexity, at the thin boundary between destruction and creation. Now, imagine these reactions happening inside or upon the surfaces of acid droplets. Each droplet acts like a microcosm, a miniature world. Molecules from the gas phase dissolve into the acid, where they meet new partners and undergo reactions that wouldn't happen in gas alone. The acid is not just a solvent, it's an active participant. It donates protons, rearranges bonds, and, in some cases, even protects fragile structures by isolating them from radiation. So, paradoxically, the very medium we think of as hostile sulfuric acid can serve as a cradle for transient complexity. What's remarkable is that these droplets can persist for weeks, maybe months, circulating through the global winds before evaporating or merging. During that time, the chemistry within them evolves. As sunlight penetrates, the outer layers react first, forming thin films of new compounds, sulfates, nitrates, or perhaps traces of organosulfur species. Deeper inside, shielded from radiation, other reactions might proceed more slowly, driven by temperature and diffusion. It's like watching two kinds of time unfold at once: fast, bright, destructive reactions on the surface, and slow, contemplative chemistry in the heart. When we simulate these conditions in laboratories, acid droplets, ultraviolet light, trace organics, the results are mesmerizing. Complex mixtures form spontaneously: thioethers, nitriles, even faint amino acid backbones. The environment doesn't nurture life, but it does test its limits. It shows us what molecules can endure, what structures persist, even when the universe seems to conspire against them. And, well, that's what makes Venus so fascinating. It's not just an end, it's a crucible. The photons that drive this alchemy come mostly from the sun's ultraviolet bands, wavelengths between 200 and 300 nanometers. At those energies, molecules absorb light and break apart in specific, predictable ways. Water splits to form hydroxyl. Carbon dioxide produces carbon monoxide and oxygen. Sulfur dioxide yields sulfur monoxide and atomic oxygen. Each of these fragments becomes a reactive agent, a spark in the network of reactions that keeps the Venusian atmosphere alive. So, when cometary material adds new ingredients to that network, it doesn't disrupt it, it enriches it. It adds threads to the tapestry, creating new pathways for transformation. Picture this: a small patch of cloud, newly seeded by the remains of an interstellar visitor. The local chemistry becomes momentarily unbalanced: too much carbon, too much hydrogen. The photons strike, reactions ignite. Within minutes, you'd see changes invisible to the naked eye but clear in spectrum: slight darkening in ultraviolet absorption, faint emission lines from CN radicals, a temporary increase in water-derived species. The disturbance would spread, caught by the superrotating winds, carried across the planet in days. And, by then, the original molecules would be gone, but their fingerprint spectral ghosts would remain. There's a beautiful irony here. Ultraviolet light destroys, but it also reveals. When molecules absorb it, they tell us who they are. They leave signatures that our instrument spectrometers aboard orbiters like Akatsuki can read from afar. Every reaction that takes place in the Venusian sky is also a message, a note in a cosmic symphony of chemistry. And when we decode those notes, we're not just learning about Venus, we're learning about the rules that govern matter itself. So, what would happen first if cometary molecules entered those clouds? The first step, well, is photolysis, light-breaking bonds. Then comes radical formation. Then comes recombination, new molecules forming in the chaos. H2O photolyzes to form O. CO breaks to C and O. HCN yields CN. Those radicals meet sulfur-bearing molecules like SO2, forming species such as OCS or HSO. Some of these compounds are stable, some fleeting, but all are meaningful. They are snapshots of chemistry, trying to find balance in a world perpetually out of equilibrium. And, that's perhaps the most important point. Venus is out of equilibrium. It's not settled. It's constantly striving, constantly changing, driven by light, by heat, by motion. On Earth, equilibrium often means peace, stability, life. On Venus, it means stasis, death. The planet resists equilibrium because equilibrium would mean silence. And yet, in that resistance, in that never-ending dance of reaction and radiation, there's vitality of another kind. If we could follow a single molecule, say, a trace of HCN from a comet as it enters the Venusian air, its journey would be astonishing. It would fall through thin gas at first, then strike the upper haze and break apart. Its fragments would collide with sulfur dioxide, form new radicals, maybe even generate short-lived chains of carbon and nitrogen. Some might dissolve in acid droplets, others might recombine higher up. Within hours, the molecule's identity would be gone, but its atoms would live on in sulfuric acid, in trace gases, in reflected sunlight. Its death would be its transformation. The sunlight itself, acts as both the sculptor and the storyteller. It decides what survives and what fades. In regions of high illumination, radicals dominate. In shadowed regions, recombination rules. The day-night cycle on Venus, though long, creates subtle chemical waves, oscillations that ripple through the clouds. During the day, photolysis dominates. During the night, the fragments seek each other out, forming more stable compounds. So the atmosphere breathes in its own way, a slow inhale of light, a slow exhale of chemistry. Some of the most intriguing models suggest that hydrogen cyanide could, in these acidic clouds, transform into molecules resembling formamide or cyanamide compounds that, on Earth, play roles in prebiotic chemistry. It's speculative, of course, but it reminds us that life's raw materials don't need gentle conditions, they only need persistence. And on Venus, despite everything, despite the acid, the heat, the radiation, persistence is exactly what chemistry seems to do best. And perhaps, that's why scientists keep returning to Venus, because in its fury, it mirrors creation itself. The same processes that once forged complex molecules on the young Earth could be happening here, endlessly undone and remade by light. It's not about life on Venus, it's about the possibility of chemistry, finding footholds in the unlikeliest places. When we look at it that way, the ultraviolet radiation that tears apart molecules isn't a villain, it's a craftsman. It chisels at matter, shaping new forms from the fragments. And the acid clouds, instead of being merely corrosive, become sculpting hands, preserving what can endure, dissolving what cannot. It's not destruction, it's refinement. It's the universe testing its own creativity. So, if cometary materials ever did mingle with Venus's atmosphere, they wouldn't vanish without consequence. They'd trigger cascades of photochemical reactions, brief but profound moments of transformation that could leave detectable traces. And those traces, might still be out there, waiting in the spectral fingerprints of the clouds, waiting for a new mission, a new eye in orbit, to notice them. And, well, that leads us naturally to the next question. If such reactions did occur, if ultraviolet light reshaped foreign molecules into something new, could any of those products survive long enough to tell their story? Could amino acids, the fragile backbones of life's chemistry, withstand such extremes? It sounds impossible. And yet, recent discoveries suggest otherwise. So perhaps the next surprise waiting in the clouds of Venus isn't about what's destroyed, but about what endures. It's strange, isn't it? That something as delicate as an amino acid, a molecule that on Earth builds skin, muscle, and memory, might survive in a world like Venus. A world where the air itself is acid, where droplets of sulfuric rain never fall, only hover and burn. For decades, scientists believed such molecules could never endure there. The assumption was simple, almost comforting. Acid kills. It breaks bonds, strips electrons, erases complexity. But, well, the universe, as always, seems to have its own sense of irony. In 2024, laboratory studies began to show something unexpected. Researchers recreated the conditions of Venus's clouds' dense sulfuric acid, high pressure, temperatures between 50 and 80 degrees Celsius, and introduced amino acids, one by one. The results were supposed to confirm what everyone thought they already knew, that organic backbones would be destroyed. But, that didn't happen. 19 out of 20 amino acids held together. Their central carbon chains, their spines, remained intact, unbroken, quietly defying the very idea that acid must mean annihilation. That, discovery changed everything. It didn't mean life, not exactly, but it did mean persistence. It meant that molecules capable of complex chemistry, capable of being part of something larger, could exist in an environment once written off as terminal. It's not that life hides there, it's that chemistry refuses to die there, and that realization forced scientists to rethink what hostile really means. If we imagine, for a moment, that cometary material water, hydrogen, cyanide, trace organics did enter the Venusian clouds, then these findings become something more than curiosity. They become context. They tell us that when ultraviolet light fractures molecules and when acid droplets absorb the fragments, not all is lost. Some structures, some patterns of carbon and nitrogen, can hold their shape even in this infernal equilibrium. The acid doesn't destroy them, it chooses among them. It's selective, like an unseen sculptor. Well, to understand why, we need to look closer at what sulfuric acid really does. In chemistry, it's known as a dehydrating agent. It pulls water away, steals it from molecules, stripping hydrogen and oxygen. In doing so, it can stabilize certain bonds. Amino acids, in their simplest form, contain both an amino group and a carboxylic acid group. When sulfuric acid removes water, it can drive these groups to form internal rings or salts that are surprisingly resistant to further attack. So, paradoxically, the acid that should destroy them ends up preserving their backbone. You could think of it as a kind of alchemical test. The fragile parts dissolve, the stable parts endure. It's not a place of life, but of selection. The planet doesn't nurture, it refines. And that, in a way, mirrors evolution itself. Not biological evolution, but chemical evolution. A sorting of forms by their ability to survive in chaos. The experiments showed something else too. When these amino acids sat in acid droplets under ultraviolet light, some began to transform. Their side chains rearranged, forming new compounds, sulfonates, nitrates, hybrid molecules that no human chemist had ever seen before. The researchers found that these transformations weren't random. They followed pathways similar to those seen in mild prebiotic reactions on early Earth. The difference was speed. On Venus, where acid and light are relentless, reactions that take months in a lab might occur in seconds, and, that makes the clouds of Venus feel less like a graveyard and more like a forge. That's the thing about Venus. It doesn't offer comfort, but it does offer opportunity. Every droplet, every photon, every molecule is forced to react, to change, to become. Nothing rests. And so, if amino acids or their precursors found their way there, carried by comets, formed photochemically, or even generated by volcanic outgassing, they wouldn't vanish instantly. They'd enter a cycle of destruction and rebirth. They'd dissolve, reform, mutate. The acid would test them again and again. And, in that endless repetition, some patterns might prove remarkably stubborn. We often think of habitability as a static condition, a temperature, a pressure, a range where water is liquid. But Venus reminds us that life, or at least chemistry that leads to life, may prefer turbulence to tranquility. Perhaps the building blocks don't need calm, they need challenge. Perhaps the furnace is as important as the cradle. In that context, the finding that amino acid skeletons persist in sulfuric acid isn't just a chemical oddity, it's a statement about resilience. It means that organic molecules are not as fragile as we once thought. They can endure, even thrive, in environments that seem utterly alien. And, well, that has profound implications not only for Venus but for exoplanets scattered across the galaxy. If complexity can survive in acid, then the window for chemistry in the universe is far wider than we dared to imagine. Let's linger for a moment on the imagery. Picture the clouds, golden white, rolling endlessly in the upper atmosphere. Inside each droplet of acid floats a few stray molecules, carbon, nitrogen, oxygen, remnants of comets or volcanism. Sunlight filters through, fragmented, shimmering. Each photon strikes, breaks a bond, rearranges a chain. For every molecule destroyed, another forms. For every pattern erased, another emerges. The atmosphere becomes a moving canvas, painting and erasing chemistry in the same breath. And, somewhere within that motion, there might exist a fleeting equilibrium, not stable, not permanent, but persistent enough for molecules like glycine or alanine to survive for days, perhaps weeks. That's long enough for detection, long enough for transformation, long enough for meaning. In 2024, when scientists analyzed the results of those Venus analog experiments, one detail stood out. It wasn't just that the amino acids remained intact, It was that their infrared absorption patterns, their vibrational voices, stayed recognizable even after prolonged exposure. That means if such molecules ever existed in the Venusian clouds, they could, in principle, be detected by future missions by infrared or mass spectrometry, perhaps from probes like Da Vinci or Envision. So the question shifted from could they survive to could we see them? It's humbling to realize that our instruments might one day read the faint signature of carbon-nitrogen bonds drifting through the acid haze of another world. That the same structures that form in our bodies could momentarily exist in the skies of Venus. It's not evidence of life, but it is evidence of possibility of continuity between the chemistry of Earth and the chemistry of the cosmos. And maybe, that's the deeper truth hidden in this discovery, that life is not a miracle confined to comfort. It's a tendency, a preference of matter to organize, to persist, to explore the edges of chaos. The Venusian clouds, with their acid and heat and light, are not exceptions to that rule, they're participants. The universe, it seems, likes to experiment. Still, we must be careful. The survival of amino acids in acid doesn't mean they form there naturally. They could be transient visitors, created elsewhere, and preserved only briefly. Yet even that brief existence tells us something crucial, that organic chemistry is not confined to the gentle and the green. It can unfold in the golden and the corrosive too. Imagine, for a moment, a comet releasing its dust, its fragments falling into the Venusian winds. Those fragments carrying amino acids formed billions of years ago, long before Earth cooled. They drift downward, caught in acid droplets, shielded from ultraviolet by the thick upper haze. They survive altered, yes, but intact enough to endure another turn of the planetary cycle. They become part of Venus's story, however briefly, and then, when the droplets evaporate, they vanish again into gas, into ions, into light. That's chemistry as a kind of reincarnation. There's a quiet elegance to that idea. The same molecules that make up the language of life on Earth might have visited Venus, tested their resilience there, and survived not as biology, but as memory. As evidence that the universe doesn't draw hard boundaries between destruction and creation. It blurs them. It lets one become the other. And, that's what makes the new research so poetic. It reframes sulfuric acid, not as a killer, but as a judge. It doesn't indiscriminately erase, it selects, it filters, it preserves what can withstand its trial. The phrase acid kills gives way to acid chooses. It's not hostile, it's discerning. This shift in understanding also echoes through planetary science. For years, the idea of life or even prebiotic chemistry on Venus was dismissed because of the word acid. Now, scientists are beginning to wonder if acid, in the right concentration, might actually help chemistry persist. Not in the way water does on Earth, but differently, through catalysis, through stabilization, through the strange balance of destruction and creation. We often imagine alien environments as obstacles to be overcome, but perhaps they're just different laboratories, different ways for the same universal chemistry to play out. On Earth, water is the solvent of life. On Venus, sulfuric acid could be the solvent of endurance. And, that changes everything about how we look for signs of complexity beyond our planet. It's not just Venus. Across the cosmos, we've detected acid clouds, sulfur compounds, and hot atmospheres around exoplanets. If the chemistry we see on Venus can preserve amino acids, even briefly, then those distant worlds may also harbor stable organic structures, tiny sparks of order in vast seas of fire. So, the finding resonates far beyond our solar system. It widens our sense of what's possible. There's something almost spiritual in that thought. The idea that matter itself, given energy, given challenge, finds ways to endure, that even in acid, under crushing light, the patterns of life's chemistry refuse to vanish. We grow older, clocks tick, worlds turn, but the molecules remain, stubborn and quiet, carrying the same, a story from one planet to the next. And so, as we trace this story forward, one question begins to form. If acid can preserve structure, what happens when metals' tiny traces of nickel, iron, cobalt enter this system? Could they act not only as survivors, but as catalysts, nudging these reactions further, faster, deeper? Could the Venusian clouds, with their acid and their metals, become a vast natural reactor, not just preserving complexity, but enhancing it? Well, that's the next step. Because in the chemistry of Venus, as in all chemistry, endurance is only half the story. The other half is transformation. And, well, to understand that, we'll have to look at how trace metals might guide the dance between molecules, how even the smallest atom of nickel or iron could, in that golden haze, become the spark that makes the impossible happen. Catalysts. Well, catalysts are like whispers in the language of chemistry. They do not speak loudly. They do not change the story itself, but they change the tempo, the rhythm with which reactions happen. They make the impossible ordinary, the slow inevitable. And on Venus, where every molecule is under tension between heat and acid, between destruction and transformation, the presence of even the tiniest trace of metal might be enough to shift everything. Let's imagine for a moment that a comet such as 3I Atlas really did brush past Venus, leaving behind grains of dust rich in nickel, iron, or cobalt. These are the quiet metals of the universe, the bones of planets, forged in the hearts of stars, cast into space when suns die. They are, everywhere, in trace amounts, and yet they carry extraordinary power. In laboratories on Earth, nickel is used to catalyze the water-gas shift reaction, the simple yet profound conversion of carbon monoxide and water into carbon dioxide and hydrogen. That process fuels industries, sustains energy systems, and, in a sense, mirrors one of the most basic balances in planetary atmospheres, the exchange between oxidized and reduced gases. Now, picture that happening, not in a reactor on Earth, but within a droplet of sulfuric acid floating through the clouds of Venus. The environment seems impossible, corrosive, volatile, but that's exactly where catalysis becomes interesting. You see, catalysts don't survive by resisting the environment. They survive by using it. They lower the barriers that prevent molecules from reacting, allowing transformations that would otherwise require immense energy to unfold quietly, even gracefully. If a grain of nickel from an interstellar comet were to dissolve slightly in those acid droplets, it might not vanish entirely. Instead, it could form nickel sulfate NiSO4, a salt that remains stable even in concentrated sulfuric acid. And in that form, it becomes something new, not just a remnant of the comet, but an active participant in Venus's chemistry. Nickel ions could interact with carbon monoxide and water molecules, perhaps forming transient complexes that guide them toward the reaction pathway leading to carbon dioxide and hydrogen. That's the same fundamental reaction that humanity uses on Earth to balance carbon cycles in controlled systems. And that raises a beautiful question. Could Venus itself, in some forgotten moment, have performed its own version of this industrial process? Could trace metals delivered by cosmic visitors have acted as natural catalysts, tuning the chemistry of the atmosphere for a brief time? We don't have evidence, not yet, but the physics and chemistry suggest that it's at least plausible. You see, catalysis doesn't require abundance, it requires position. A single atom of nickel, if placed in the right molecular neighborhood, can trigger thousands of reactions before it's spent. The Venusian clouds, filled with billions of acid droplets, each droplet containing millions of reactive molecules, provide endless neighborhoods, endless chances for chemistry to meet opportunity. And when you combine that with constant sunlight, constant motion, and constant renewal, you have something that behaves less like a dead atmosphere and more like a living chemical engine. Well, there's something almost poetic about that. Venus, the so-called planet of death, might also be a planet of catalysis, a place where metals from space fall into acid and awaken dormant reactions. The acid doesn't dissolve them into nothingness. It converts them into mediators, into conductors of molecular symphonies. In industrial chemistry, nickel catalysts work because they offer surfaces where molecules can meet. They absorb carbon monoxide on one side, water on the other, and in that confined space, bonds rearrange. The products carbon dioxide and hydrogen depart, leaving the catalyst ready to begin again. Now, In Venus's clouds, there are no solid reactors, no metal walls, but at microscopic scales, some of the same principles might apply. Nickel ions could cling to acid droplets, forming microenvironments where reactions are guided more efficiently than they would be in open gas. What's remarkable is how universal that principle is. The lowering of activation energy, the creation of pathways through otherwise impassable barriers, that's what makes catalysis so powerful. It's what makes life possible too. Enzymes in our bodies are catalysts made of proteins and metals. They too transform energy barriers into gentle slopes. So, in a way, thinking about Venus as a catalytic world is not just scientific, it's philosophical. It reminds us that even without life, matter can organize itself to accelerate complexity. But how would we know, really, if such catalysis occurs? The answer might lie in the signatures left behind. If nickel were acting as a catalyst in the Venusian clouds, we'd expect to see subtle imbalances slightly more. Hydrogen than expected, small shifts in the ratios of CO and CO2, faint changes in how light interacts with the clouds. These would not last long, of course. The superrotating winds would mix and erase them within days, but for those few days, the planet's chemistry would hum a little differently. The idea of comet-derived metals acting as catalysts also fits within what we know of cosmic dust. Many interstellar grains contain nickel-iron alloys. When these enter planetary atmospheres, they oxidize, fragment, and sometimes dissolve into ions. On Earth, such events contribute trace metals to the upper atmosphere, influencing ozone chemistry. On Venus, with its denser and hotter air, that effect could be magnified. And, well, even if it lasted only briefly, it could spark reactions that ripple through the layers of the atmosphere, like echoes of a forgotten visitor. It's worth noting, though, that this isn't mere speculation without foundation. The catalytic behavior of nickel in acidic and high-temperature environments is well documented on Earth. In certain industrial processes, nickel-based catalysts operate in sulfuric acid solutions at elevated pressures and conditions, not entirely unlike those in the Venusian clouds. So, while the specific combination of acid, sunlight, and cosmic dust might sound exotic, the underlying chemistry is familiar. It's an extension of principles we already understand. Still, there's a mystery in it. On Earth, we design our reactors with precision. On Venus, nature has to improvise. Droplets drift, metals dissolve unevenly, sunlight flickers through the haze. The chemistry unfolds in fragments, in waves, in chaos. But even chaos has patterns. And perhaps, just perhaps, those patterns have left faint fingerprints, spectral traces of metallic sulfates or hydrogen-rich regions waiting to be detected by future missions. You know, there's something deeply moving about the thought that the same element we use to refine fuels and build technology could also act as a silent craftsman in the clouds of another world. It's not just coincidence, it's continuity. The periodic table is a universal script, and Venus is reading its own lines from the same page. And when you think about it, this idea of catalysis blurs the boundary between the living and the non-living. A catalyst doesn't live, but it behaves as if it understands. It senses imbalance and corrects it, not by intention, but by physics. It allows energy to flow more smoothly, structure to emerge more quickly. And if Venus's atmosphere really does host such processes, then it might be the closest thing to metabolism a lifeless world can have. In that light, the role of metals becomes almost mythic. They are the connectors, the translators between states of matter. Iron, nickel, cobalt. They move through the cosmos as fragments of stars, carrying with them the capacity to catalyze, to awaken, to link. When they fall into Venus's acid, they don't die. They begin their work again, quietly, invisibly. And, perhaps that's one of the ways the universe keeps itself busy, through endless small acts of catalysis. If we ever manage to send a probe capable of directly sampling the clouds, something like Da Vinci or Envision might attempt in the years after 2025, it could look for these metallic species. By measuring the ratios of nickel, iron, and their sulfate forms, we could test the hypothesis that catalysis plays a role in Venus's atmospheric chemistry. If we find even a slight excess of certain products like hydrogen or carbon dioxide in regions where metal concentration is higher, that would be a clue, not proof, but a whisper of confirmation. And, imagine what that would mean. It would suggest that planets can momentarily alter their chemistry, not just through heat and radiation, but through the gifts of passing comets. It would mean that the boundaries between interstellar and planetary chemistry are porous, that the universe is one continuous experiment, with materials from one world influencing another in ways we're only beginning to understand. In that sense, the arrival of Cometary nickel is not just an event, it's a connection. It's a reminder that even the smallest atoms, scattered across space, can link stories billions of years apart. A star explodes, creating nickel. That nickel condenses into dust, travels through interstellar darkness, finds its way into a comet, and eventually meets the acid clouds of Venus. There, it dissolves, catalyzes a few reactions, and becomes part of the planet's atmosphere. And, perhaps some of its atoms will one day drift back into space again, carried by the solar wind, waiting to start the cycle anew. There's a quiet elegance to that vision. The metals of the universe are not inert, they are the artisans of transformation. On Venus, they may be shaping chemistry in ways that echo across cosmic time. It's not just a question of what reactions happen, it's a question of what they allow to happen. And so, we find ourselves standing at the edge of another possibility. If these trace metals can act as catalysts in the acid clouds, then they can also change how we read the planet's spectrum, how we interpret its signals. Subtle variations in absorption could reveal zones of catalytically active chemistry regions where the atmosphere behaves almost intelligently, optimizing itself. Well, that brings us to a natural next question. If Venus's clouds can, even for a short time, host reactions catalyzed by alien dust, if the planet itself can borrow the chemistry of the stars, then what visible traces would those reactions leave behind? Could we detect temporary surges in hydrogen, in carbon monoxide, in the fine structure of cloud droplets themselves? Could the winds carry those signatures around the planet like a fleeting fingerprint of an encounter? And, well, that's where the story flows next to the predictions, the observable hints, the measurable echoes that might tell us if this quiet chemistry between worlds ever truly happened. If Venus truly borrows the chemistry of the stars, well, it must also leave behind a signature, something faint, fleeting, but measurable. Every reaction, every collision, every whisper of transformation writes a mark into the light. And it's in that light, that scattered sunlight filtered through acid and metal and motion, that we might find the evidence. You see, planets speak through spectra. Their clouds and gases absorb and reflect specific wavelengths, turning sunlight into a language of color and shadow. If cometary dust and catalysis ever danced within the Venusian clouds, the traces of that dance would shimmer there, hidden, but not lost. Imagine looking at Venus through a spectrometer. The light from the sun passes through the planet's atmosphere and bounces back toward us, carrying the fingerprints of every molecule it met along the way. Each molecule, carbon dioxide, sulfuric acid, hydrogen cyanide, even transient radicals like CN or OH, absorbs a tiny distinct fraction of that light. When scientists spread the light into a spectrum, they see not a smooth rainbow but a landscape of valleys, each one a clue. And so, to find the echoes of cometary interaction, we must look for valleys that don't belong, spectral dips that appear for a moment and then fade, as if the planet itself were remembering something. The first hints might appear in the infrared, where molecules like water and carbon monoxide sing most clearly. A sudden excess of water vapor, even if only for a few days, would stand out like a brief heartbeat. It would not last. Venus's heat and acidity would destroy it quickly, but while it did, it would alter the balance of infrared emission. The planet's thermal glow would shift, slightly, subtly. And if we were watching, with instruments sensitive enough like the future orbiters planned after 2025, we might catch that change. That whisper of hydration in a desert of acid. Then there are the ultraviolet patterns, the dark bands that have haunted observers for decades. These mysterious streaks, seen by spacecraft like Akatsuki, absorb ultraviolet light in uneven patches across the cloud tops. Their cause remains uncertain. Some propose sulfur allotropes, others suspect iron chloride or complex organics. But, well, if cometary metals and organics ever mixed into the upper clouds, they might have contributed to these absorbers. Transient compounds formed by nickel or iron reacting with sulfuric acid could darken the clouds in localized regions, forming patterns that drift and dissolve with the winds. If those patterns changed following the path of a cometary encounter, if they appeared suddenly, only to fade weeks later, it would be like watching Venus blush and forget. And, even the winds themselves might carry clues. The superrotation that drives Venus's atmosphere acts as both eraser and messenger. Any disturbance, a new compound, a shift in density, a pocket of altered chemistry would spread rapidly, encircling the planet in mere days. The result wouldn't be a fixed spot, but a moving wave, a subtle modulation in how the clouds reflect sunlight. Scientists might detect it as a rhythmic variation in brightness, a pattern that circles the globe faster than the planet's rotation. That pattern could be the fingerprint of motion caused by energy released during chemical change, tiny reactions powered by the infusion of foreign material. The idea sounds poetic, but, it's grounded in physics. When new compounds form in an atmosphere, they can change how heat moves. A cloud that absorbs more sunlight in one region warms differently than the clouds beside it. That temperature difference drives circulation, and circulation reshapes the clouds again. So chemistry becomes weather, and weather becomes signal. The fingerprint of a cometary encounter wouldn't just be chemical, it would be dynamic, alive. There might also be evidence in the subtle fluorescence of Venus's airglow. At night, when the sun sets and the upper atmosphere cools, molecules like oxygen and nitrogen emit faint light as they recombine. The color and intensity of this glow depend on what molecules are present. If cometary material added extra hydrogen or carbon, the glow might briefly change, becoming slightly brighter in certain bands, slightly dimmer in others. It's as if the planet exhales the memory of what it swallowed during the day. You know, what's haunting about all this is how transient it would be. These changes would not last centuries or even years. They'd pass in days, maybe weeks. The atmosphere would mix, the winds would smooth everything out, the traces would vanish into the planet's constant churn. But in that brief window, if we were watching closely enough, we might glimpse the evidence of an interstellar visitor's touch. And, that's what makes it so difficult and so beautiful. The universe doesn't leave permanent signatures, it leaves gestures. It speaks in moments. Modern instruments are beginning to catch up with that kind of subtlety. The upcoming Envision mission, for example, will carry radar and spectrometers capable of probing the atmosphere in unprecedented detail. It could detect anomalies in trace gases, small deviations from the expected balance of carbon dioxide, sulfur dioxide, and water. And if, well, those deviations correspond with regions of unusual ultraviolet absorption, it would hint that chemistry, catalysis, and light are entwined in ways we hadn't imagined. The idea of spectral echoes is not new. On Earth, scientists track the after effects of meteor showers by observing how metals like sodium and iron linger in the upper atmosphere. They can measure how those elements scatter light, even days after the meteors themselves have burned away. The same could happen on Venus. A passing comet might leave behind a faint metallic haze atoms of nickel, iron, magnesium that drift in the upper layers, forming a reflective or absorptive veil. That veil might change the planet's brightness slightly, enough for sensitive telescopes to notice. And, well, perhaps we've already seen it, without knowing. Perhaps some of the unexplained brightness fluctuations recorded by past missions were not mere instrument error, but the fading memory of such encounters. It's humbling, really, to think we might have brushed past the evidence of cosmic chemistry and never realized what it was. The key, of course, is timing. To catch an event like that, we'd have to observe continuously, not just in snapshots. We'd need instruments watching Venus day after day, looking for spectral lines that appear, shift, and disappear, a slight uptick in water vapor, a temporary increase in hydrogen cyanide, a faint glow in the near-infrared. These would be the signatures, the planetary size, of a brief but profound interaction. But Venus is not an easy target. The very clouds that hold the secrets also hide them. They reflect so much light that the planet becomes a mirror, its own brightness drowning out faint details. It's like trying to read handwriting on the surface of a flame. Yet, we've learned to do it, to listen for the faintest whispers in the light. Instruments aboard Earth-based observatories, orbiting telescopes, and even high-altitude balloons could all play their part in unraveling the story. Some of the most promising clues might come from the chemistry of sulfur itself. When ultraviolet light and trace metals interact with sulfuric acid, they can produce unusual sulfur oxides and sulfates. These compounds absorb light differently, creating small deviations in the ultraviolet spectrum. If we detected new sulfur species forming and fading, it could point directly to catalytic reactions involving nickel or iron. And, those reactions, in turn, could have been sparked by foreign dust from a comet's tail, dust from the stars. The possibility becomes even more compelling when you realize that Venus's atmosphere is already unstable in subtle ways. It contains just enough sulfur dioxide and carbon monoxide that, in theory, they should react and balance out. Yet they don't. Something keeps resetting the chemistry, preventing equilibrium. For decades, scientists have puzzled over this, wondering if volcanic outgassing or photochemical processes might be responsible. But, well, what if some of that imbalance comes from periodic external inputs? Small doses of cosmic material entering the clouds and stirring the reactions anew. If that were true, it would mean that Venus's atmosphere is not a closed system at all, but a porous one, a system open to the universe, breathing in dust, exhaling light. The chemistry we observe would then be a mixture of the planet's own metabolism and the infusions of interstellar matter. That's not just an atmospheric model, it's a worldview. It suggests that even planets are not isolated. They participate in the grand exchange of the cosmos. And perhaps, that's what makes Venus so captivating. It's not just that it's beautiful or hostile, it's that it's connected. Every drop of acid, every swirl of wind, every spark of reaction might carry atoms from distant stars. When we study Venus, we're studying not only a planet, but also the dialogue between worlds. If the next generation of missions could confirm even one of these predictions, a spectral deviation, a metallic trace, a fleeting surge of hydrogen, it would rewrite our understanding of planetary chemistry. It would prove that cosmic encounters leave measurable echoes, that interstellar material can shape the behavior of entire worlds. It would mean, that planets are more like memories than machines forever rewritten by what passes through them. And yet, for all the complexity, the beauty lies in the simplicity of it. A comet passes, a few grains of dust fall, light strikes, bonds break, bonds form, the atmosphere stirs, and for a moment the planet changes. It's not dramatic, not catastrophic, but delicate, a cosmic sigh, a gesture of transformation so quiet that only instruments and imagination can hear it. Well, if we're lucky, in the coming years we'll have those instruments. We'll watch the clouds of Venus more closely than ever before, listening for the subtle harmonies of chemistry and light. And when we do, perhaps we'll begin to see not just a planet, but a pattern, a recurring rhythm of change linking Venus to comets, to interstellar dust, to the deep processes that shape every world. And that thought, leads us naturally forward to a larger question. If Venus's atmosphere can capture the memory of encounters and translate them into light, then what about other planets, other worlds bathed in the same starlight? Could they, too, carry echoes of cosmic touch patterns written in air and reflected in time? And, that's where we'll go next. To truly see what Venus is doing, we need instruments, not just the eyes of imagination, but the eyes of precision. The kind that can look through clouds, thick as oceans, and listen to light itself. Venus, doesn't give up its secrets easily. Its glare blinds telescopes, its heat destroys landers, and its atmosphere bends and scatters every signal we send its way. Yet, for more than half a century, We've been listening, watching, and guessing, turning photons and radio waves into stories about what happens in that golden haze. Now, the challenge is sharper than ever. The current generation of missions has done what it can, but to confirm the faint, spectral echoes of interstellar chemistry, to test whether the planet has ever borrowed the dust of a wandering comet, we need new eyes in orbit, and perhaps, one day, in the clouds themselves. Akatsuki, the Japanese orbiter that gave us some of the most beautiful ultraviolet images of Venus ever captured, has finally fallen silent. It lost contact in April of 2024, and by September 2025, its mission was declared complete. It left behind a legacy of light data that continues to speak long after the spacecraft itself went dark. And yet, Akatsuki was never built to answer the question we're now asking. It watched the planet's weather, its winds, its patterns of brightness. It revealed the mysterious ultraviolet bands that pulse across the clouds, but it couldn't tell us what those streaks were made of. To find the fingerprints of cosmic dust, to see the faint shimmer of metallic ions or transient water vapor, we'll need to look differently, to listen at more wavelengths, deeper and longer. That's where the next generation comes in. NASA's Da Vinci mission, Deep Atmosphere, Venus investigation of noble gases, chemistry, and imaging, is planned to dive directly through the planet's atmosphere. It will fall, like a slow-motion meteor, sending back data as it descends. For a few precious minutes, Da Vinci will sample the air from 60 kilometers down to the surface, measuring gases, droplets, isotopes, the very ingredients of Venus's chemical story. If cometary dust has ever left its mark, Da Vinci's instruments might find traces of unusual isotopic ratios, tiny differences in hydrogen or carbon that whisper of an origin beyond the solar system. Then there's Veritas, an orbiter designed to map the planet's surface with radar so sharp it can reveal mountain ridges and volcanic scars beneath the clouds. While the goal is geology, its instruments can also sense heat, emissivity, and spectral hints from the atmosphere itself. If the chemical balance of Venus's air shifts temporarily, say, from the arrival of external material, Veritas might notice faint anomalies in the infrared, like a change in how the planet glows at night. And, further on the horizon, the European Space Agency's Envision mission will take up the torch. Envision is a hybrid, a mapper, a listener, a watcher of both surface and sky. Its spectrometers will peer into the atmosphere with extraordinary sensitivity, tracing the fingerprints of carbon dioxide, sulfur dioxide, and, perhaps, transient species like hydrogen, cyanide, or formaldehyde. If there are any temporary increases in these compounds, if the chemistry of Venus still remembers the touch of an interstellar visitor, Envision might be the one to catch it. But, well, even before these missions arrive, the search has already begun here on Earth. Ground-based observatories, equipped with radio and infrared telescopes, like ALMA in Chile and the Infrared Telescope Facility in Hawaii, are watching Venus from afar, tracking its spectral heartbeat. They can't see as deeply as orbiters, but they can see change. Over days and weeks, they can detect shifts in gas concentrations, fluctuations in brightness that hint at chemistry in motion. It's difficult, painstaking work, balancing signal against noise, light against distortion, and yet, that's where discovery often begins, in the noise, in the uncertainty. The tools we use are as delicate as the signals we chase. Spectroscopy, radio occultation, thermal mapping, each one is a language. When a spacecraft passes behind Venus, its radio signal bends through the atmosphere, slowing and dimming. From that distortion, scientists can reconstruct temperature, density, and composition profiles. They can tell where sulfuric acid droplets thicken, where heat builds, where gases mix. It's like listening to a voice through water and still understanding the words. And if, by some miracle, a new compound, a trace metal salt, perhaps, or an organic molecule altered the refractive index of the air, we would see it. Not directly, but as a change in how the signal trembles. The technology has evolved far beyond what early missions like Pioneer or Venera could have imagined. The sensitivity now is such that we can detect parts per billion of certain gases. the spectral ghosts of molecules that exist only briefly. In 2025, the line between imagination and measurement is thinner than ever. We can almost hear the chemical conversations happening in Venus's clouds. But we must be careful, always careful. The history of planetary science is full of false dawns, signals mistaken for miracles. The phosphine debate, for instance, taught us humility. In 2020, researchers announced possible traces of phosphine gas in Venus's atmosphere, a molecule often associated with life. The news raced across the world. Then came skepticism, reanalysis, recalibration. The signal weakened, the certainty faded. It wasn't proof of life. It was proof of how difficult it is to read a world through light. And yet, that debate reignited interest in Venus. It reminded us that even a null result can awaken wonder. So, when we speak of searching for cometary echoes, when we imagine detecting traces of nickel, hydrogen, cyanide, or transient organics, we must remember that these are delicate pursuits. The signals will be faint, the interpretations complex, but the very act of looking will deepen our understanding, because every measurement, even the quiet ones, reshapes the boundaries of what's possible. The beauty of modern planetary observation lies in its diversity. No single instrument can tell the full story. It takes a chorus: radar for shape, infrared for heat, ultraviolet for chemistry, radio for structure. Together, they weave a multidimensional image, a planet not as a static sphere, but as a living, breathing system. And, within that tapestry, even the smallest anomaly, a blip of unexpected water, a glimmer of hydrogen, could be the key that connects Venus to the wider cosmos. Ground-based campaigns will also play a vital role in bridging gaps between missions. Networks of telescopes, working together across continents, can monitor Venus's atmosphere continuously. When Da Vinci or Envision are still months away from launch, these observatories will already be gathering data, setting the stage. They'll tell us how the atmosphere changes with time, how the winds carry heat and chemicals from dayside to nightside. And when, new spacecraft finally arrive, their findings will fit into a timeline that stretches across decades. It's not just about Venus, of course. The same methods will soon be used to study exoplanets, worlds orbiting distant stars, whose light we can only catch as a faint dip in starlight. There, too, we'll use spectroscopy to decode atmospheric composition, to ask whether acid clouds or metallic hazes might host the same kind of chemistry we're now beginning to suspect on Venus. The lessons we learn here will ripple outward, guiding how we search elsewhere. And well, perhaps that's the quiet power of these missions. They remind us that exploration isn't always about going farther, it's about looking deeper. Venus is close, almost uncomfortably close, yet its mysteries are as vast as any exoplanets. Each measurement, each spectrum, is a way of listening not just to a planet, but to the universe's ongoing experiment with matter and light. It's astonishing, really, how much we can infer from photons alone. The tilt of a spectral line tells us about motion, the width tells us about temperature, the depth tells us about abundance. It's like reading a diary written in wavelengths. And, somewhere in those pages, perhaps, lies a sentence written by a comet, carried across time and acid and fire. So, as we look toward the future, the years when Da Vinci dives, when Envision listens, when ground observatories keep watch, we're standing at the threshold of proof. Either Venus's chemistry will reveal those interstellar fingerprints, or it won't. Either way, we'll learn something profound, whether planets truly remember the touch of what passes through them. And that leads us naturally forward to the comparison that waits just beyond. Because if Venus can process, can cook whatever enters its skies, then what about Mars? What about a planet that preserves instead of transforms, that stores rather than stirs? The contrast between them is more than geological, it's philosophical. And, that's where we'll go next. When we look at Venus, well, we see transformation, a world that never stops moving, never stops reacting. It's a planet where chemistry is alive, ferocious, fluid, and fast. But when we turn our eyes toward Mars, we see something very different. We see stillness. We see preservation. If Venus is a furnace, Mars is a freezer. And, that contrast tells us something profound about how planets remember the things that touch them, how they either rewrite or record the traces of cosmic events. Venus processes everything that enters its